I have updated it. I now have some also information on 4.6 online. A couple things that are there that, or should be there that aren't. Know what the mean value theorem says, and know that when you prove it, you have to list the fact that you use Rolle's theorem. Okay? That is a required step. When you make the step using Rolle's theorem, make certain it gets stated. So, and if anybody needs extra work with a review, I'm available after school the next couple of days, and also tomorrow morning. I'll be there again tomorrow morning. Will you hand in your assignment, please, that we're working on for today? Get that handed in. I'm giving these back so that some of you maybe have some things on there that you wanted to take a look at. Okay. Today we're going to work on a little bit more L'Hopital's rule, and you know some of those things about it already, and so here we go on this one. I did a little more this year than I did with you last year with this, but this is the end behavior of rational functions. Okay? In other words, horizontal asymptotes. Now this thing right here has a horizontal asymptote at what value and why? We called it last year end behavior or asymptotes, and really what we're doing here is taking the limit of this thing, the limit as x approaches infinity. Nope, -7 is not the answer. You're in the wrong end.
3/4.
3/4. Okay?
Oh, yeah.
Are you with me on this? Because we're going to build on it now. And then those of you who take Calculus 2, when you get into Taylor series area, you will again work with L'Hopital and go back to it. And there, I don't know about this book. I would assume it does it like other books that I've taught, where it'll refer you back to the lesson we're doing for today. Okay, now, that's that way. Now let's do a few more here. What happens when this is going to be a 4? Thank you. If this is a 4. Now, where's the end behavior?
0.
Okay, got it? A 0. The limit of this thing is going to be equal to 0. All this here down here. Now that's what you're going to be looking at today. Are they going to 0? Where are they going? Okay. How about if it's a 5? It's still 0.
What if the top one's 0?
Okay, what about that way? So you're wanting to go this way, and at this point I'll just erase this like this. What happens now?
Infinity.
It goes to infinity.
And beyond. Okay.
No, just infinity, not beyond, because we don't know if there's anything there.
That's count 4.
Okay? Now, this one, with my Algebra 2 kids, I took them through a section which said it was through an oblique line, a line that's going up in a straight line like this. Not one like this, it's going this way. If they're differed by 2, it's going to be a parabola sort of shape. But, so this one, it's going to go to infinity. It gets to be infinite. Okay, now, what I'm trying to tell you here, when you have that, this one is going up at a faster rate than this one if I'm going to separate the two parts. This one's going up faster than this one. And we're going to do some things by comparison now to show that some of this is happening. Now, I wanted to do this so that we're ready to build on it for some more things. So, what I'd like you to do is go to page, well, before we get into this totally, let's first go to page 283. We're going to go through this fast. We could spend a couple of weeks just on this section, but we're just going to finish it today and go on. The stuff, if you need it, when you need it, you can come back here and get it. Notice on the bottom of page 283, you have indeterminate form this way. We have looked at indeterminate form this way, and now we have this indeterminate form. Okay? Now, those are the two driving forces in 4.14. Now, flip the page and look at the middle of the page, example 4, or just above it. You have this in this form, times 0 times infinity. That's indeterminate form. And to work it, you have to get it back into this form. There are so many things in mathematics that you have to start shifting around. And so we'd have to work to get it into this kind of form, or that, either one of the two. So that's that one. And then he also has this one. Infinity minus infinity. What is that? Nothing? Could be infinity. Could be something in between. Okay? And so that's indeterminate form. You have to take this thing and try to get it into one of these two forms. Okay? And there are nice techniques for that. And then on the bottom of page 285, he has some other really cool indeterminate forms. 0 or 1 to infinity. That's indeterminate. You'd think, hey, that has to be 1. You with me on that? Okay? And then the next one is 0 to the 0 power. That's indeterminate form. You don't know where you're at there. Okay? And the other one is infinity to the 0. Now those are really exciting kinds of things, but many times you have this and you can put it in this form with some techniques. Yes?
What about 0 to the infinity?
What about this one? I think that one would flow too, but I don't believe he has it here, does he? That's nice. Before I go too far on that one, it sure looks like it should go, but it does not have it listed here, so I'm a little cautious. Okay? So, now, we're not going to spend the time to do these. It would be interesting and nice, but we're going to stick with these two in terms of what we're doing. Okay? Now, the next one I want to do is to go to the, where am I going to go next? The theorem on page 288. Theorem on page 288. Notice what it says. It says very much like this, what we have right up here. That's what it's talking about. Growth rate of functions. And it says, suppose f and g are functions with the limit there and the limit of there. Then f grows faster than g. F grows faster than g if you get a 0. Notice that? That's the first part. Any questions about that? We're going to take a look at a couple of those. Okay? Maybe I ought to just stop there a minute and work. Let's do it. Yes?
Is this on our test on Thursday or not?
So the next one.
So
Not on Thursday. No, this isn't Thursday.
Okay, so just 4-6.
Yes, right. Got that, everybody? A couple of you came in late. Make certain you know how to prove the mean value theorem using Rolle's theorem, and where you use Rolle's theorem, make certain you're letting me know that. Okay? So here we go. Let's try this one. The limit as x approaches infinity of ln of x all over x to the p. And p is greater than 0. Okay, now, you have done some of this kind of stuff before where it's important to know if something is converging or not. We did it when we worked with a problem like this. 1/2 plus 1/4 plus 1/8 dot, dot, dot is equal to how much?
1.
1. And the ratio had to be between positive and negative 1. Had to be a fraction between positive and negative 1. Any questions about that? Then it was converging, okay? And in that case, we have to find out sometimes if things are converging, and therefore we're going to use this to see if it's going to go to 0, or if it's going to blow up on us, okay? And so now let's take a look at this, and we're going to use L'Hopital, okay? And when we use L'Hopital, and we're going to look at some problems with of that too in just a moment, I'll take the first derivative. But now, is this in the indeterminate form? As this goes to infinity, this turns out to be a 0, you know, this is infinity, and this is infinity. See that? We have infinity over infinity. Questions on that? No questions? Okay. Now, so I'll take the derivative of this, and that's 1 over x all over p x to the p minus 1. Okay? For some reason, Stewart in his book uses p just like this guy does in terms of figuring this out. Okay, now look what this turns out to be. Now I'm just going to simplify, and this x is going to be part of over here, so I have 1 on the top of here, and then I have p to the x to the p again. Now, because see, there's 1 short here, I'll make this one fill that hole. You with me on that or not?
Yeah.
DeVries, you're shaking your head. I'm going to put this downstairs, so it's going to be 1 over like this, x to the p minus 1. And this, oh, this is a minus 1. Nope, not either. It's positive 1 because it was a 1 up here, down here already. Okay, now I'm going to put that one in here. So this is going to be p x to the p because 1 minus 1 is 0. Okay? Now, at this point, can I evaluate that?
No. What? 0.
This is going to be a 0, isn't it? If that's a 0, what does this tell me? That tells me this one is growing faster than faster than the other one. This one's going fastest. Now, if you graph these, it would be pretty obvious. Now, notice p can be any number that's positive, which is rather interesting that that's the case. Now, I'm going to graph this way, and I'll first graph this one, and that goes this way, like that, okay? And this one, when p is 1, is going to be like this. Look at how this is growing up so much faster, okay? Now, it gets rather interesting. What happens if this is a half or a fourth? That's when you really get some interesting things, when you have it going way this way. Very little slope. Well, how far do you have to go out before it starts where one is bigger than the other? It's another question you could ask. So, at this point, we notice this one grows faster than this one. Okay? Now, let's go back to that theorem. It says or. We got up to the or. Or equivalently, you notice that then it's going to infinity. And notice the difference? Tell me what difference you see there. Did you hear the flip-flop? Any questions on the flip-flop? Okay, if there's no question on the flip-flop, we'll go on. Now notice the next part. It says if they equal an m, then they're comparable. Oops, I shouldn't have erased this up here. You know, the first question I had up there, it was equal to 3 over 4. They're comparable. They're going up, they're both going up, and there's a comparable rate of growth.
What's that mean? Like they're even for rate of growth, like if it raises 1, or if it goes over 1, it raises 1?
Whatever one is doing, the other one is doing way out there. Equally, yes. Like 4/3. They're approaching 4/3, and they're both going there, yes.
Is that like, so the powers are the same, so it's like x to the third over x to the third?
Did you hear that? Now that's a nice little easy polynomial one, or rational function, a polynomial over a polynomial. And those are always so nice to work with, okay? But we're not going to work with just all those kind of nice ones, are we? We aren't even going to look at them here, because we know that already, okay? Now, I have one more to do, and that's to show you a technique, and you will use it in one of your problems. Have I finished that definition? Yeah, that's pretty good there. Okay, now how about this one? We're going to go the limit as x approaches infinity of ln of, no, that's not one. We're going to go x to the p over e to the x. Okay, now, you should be pretty suspicious already that this is the one that's got the power. Because these are exponents. And exponential is the one you usually use to really say things are moving. Okay? Now, which one is going to move the fastest? And if it's going to go to 0, which one is bigger?
E to the top.
The bottom. If this is going to go to 0, it's going to be if it's going to infinity, the top one is going faster. Make sense? Just logical sense? If anybody needs more help, please speak. Because I have a little time for that.
Can you say that one more time?
Okay, if this thing goes to 0, the bottom one is growing fastest. If it's going to infinity, then that's my dog.
Hello, Mr. Kramer.
What brings you here?
Hope. I need hope.
Oh.
Yeah, I need hope in my life.
Okay, you need her for a minute?
No, I just need to deliver a camera that I forgot to give to your mother in the excitement of my daughter's engagement.
Okay.
Mr. Kramer is going to be a grandfather-in-law.
Okay. Yeah, we'll see you. Okay. After all this excitement, you see what's happening here? If this one is growing fast, it's going to be something big over something little, so it's going to go to 0. Okay? Now, to work this thing, we do this little tricky move, which is pretty wild. We're going to say x here, this x is going to be equal to ln of a t. Why? I'll show you in a minute. It's a mathematical technique. Okay? Now, with me, so you see what's happening here. If x is going to infinity here, then pretty soon t is going to go to infinity. We're going to have t going to infinity here. Watch what happens. I'm going to change this thing now to make this the limit as t approaches infinity. And when I put this in here, this is going to be ln of t to the pth power here, all over, and this turns into e to the ln of t. Are you with me?
Yeah. Right.
And the next little move, you're going to see why.
All right.
This gives me the limit as t approaches infinity, and this turns into what? What is this?
T.
That's a t. All of you got that?
No.
If you are all getting it, that's amazing.
No.
Okay?
OMG.
Okay, E and LNs are inverses of each other.
Yes, got that.
Okay? And so that's what makes them happen that way. I can give you more information to make that happen, because this is how I used to have to do it. I say y equals e to the ln of t like this, and then, yes?
How do you know that you have to make x and then equal to the ln of t?
Here?
Yeah.
Just have to know that. There is no mathematical thing you can crank it out. It's just something you have to know.
It's like that one.
Okay?
Memorize it.
And yeah, okay. Now, so this here now becomes, I could also write this way with the p here, with a t. But now this here is very similar to what I had just a few minutes ago. Then I had something very much like that here. Now, at this point you might say, which I tried this morning, I said, okay, I'll just use L'Hopital. It's infinity over infinity, so it's L'Hopital. And this is one, and I'll show you in a minute that here's a problem. The longer I worked, the more into trouble I got. It became more and more difficult every step. Every step it got a step worse. And then you know you're going in the wrong direction. So then you have to try something different. Okay? And so this is the technique if you're not going to use that previous theorem I had, or that previous problem. The previous problem I answered this. Okay? And that problem, it had p greater than 0, and in this case, the exponent here is 1. So it should work. No problem at all. But now, if you don't do that, then what I'm going to have to do is take the pth power, 1 over p like this, and 1 over p like this, like that. See that? Then this function becomes like this, t approaching infinity, of ln of t all over t to the 1 over p that way. With me? Now I'm going to do the same thing I just did a minute ago. That show this, see, this is infinity over infinity again, yes?
Why did you do the 1 over p?
Oh, I did this time the top and the bottom, power.
Well, why?
Because I wanted to get this out of here.
Oh.
I wanted to get down to this level.
Okay.
Okay? Now I'm going to take the derivative of this thing, and I get t approaching infinity, and this becomes 1 over t, and this becomes 1 over p times t to the 1 over p minus 1. Okay? And now this becomes a limit, 1 up here, t approaching infinity, and this is 1 over p, t to the 1 over p. Now I can evaluate that. The top is a 1, the bottom is an infinity, so this is a 0. So that means all the way back here, this one's growing faster. Yes?
Where did the t in the numerator go?
I took the derivative of each.
Oh, okay.
Oh, here I took the derivative, and this t, this here t went down and took care of this thing over here. Okay? Now, let's go to page 289, and there's an interesting theorem. And I just want to point it out to you. You'll work a few of these problems for me. Theorem 4.15, look what it says. If you want the order of growth, here they are in this little theorem. And let's take a look at those. And this is the one that's grown like crazy. That's the fastest one. Okay? And below it is b to the x. No matter what b is. This one would be growing slower than this one. Okay? And the one before that one is b to the p, b plus s. Okay? Now, we can look at those in more detail, but pardon?
It's x to the p plus s.
Okay, gotcha. Yeah, right. X to that, and it says p's, q's, r's, and s's are all real numbers, and b is greater than 1, which we kind of knew here anyway. So you probably had a little clue on some of this. It's not going to be required that you know it. But the theorem is here if you wanted to just check which one is growing the fastest, but also we're just doing some of them using L'Hopital. Okay? Rate of growth. Okay? Now, a major shift in thinking. So here we go. What I'd like to do for the rest of this period is undo most of the stuff we've been doing since January. Okay. And I'm going to say this. I have function f of x equals f of x, which equals x or 2x, like this. Okay? Now, this is what this is saying. I have a function here, capital F, whose derivative is this, and is this. What's my function f of x?
X squared.
That was way too fast.
No.
Okay, did you see that? Okay, who wants me some more discussion on that? Okay, I'm showing you the capital which we often use, and here. Okay, now, boy, that was fun that you guys had it that fast. Okay, f prime at x equals 3x squared. Yes, I'm just going to skip that step to go. What's f at x? Okay, how about this? You gave me that answer. But isn't this also the truth? Could that be it too?
It could be.
Oh, good. How about this number?
Yeah. Even a 3 would work.
Oh, degrees, nice. Okay, so this is how we do this. And we only do this for a couple of days. And then after that, these are called, in a moment I'll show you, indefinite intervals. And then we always write it this way, plus a C. Okay? But only for a few days are we going to do this, because we're gonna wash that thing up and get rid of it. But at this point, we have to do that. And yes, C is a constant, any constant. Okay? And you've had a couple of problems that deal with this. Problem 24 and 25 of a couple days ago, we had things looking at are their derivatives equivalent, and that's what he was getting you ready for this. Okay. How about this one? F prime at x equals e to the x. What's my function?
E to the x plus c.
Okay. How about this one? F at x, f prime at x equals x to the fourth. Over in the front here we have this. X to the fifth over 5. Okay, now this is where many of you are going to have to go. You're going to guess it and see if you're right. Okay? Now, here's the process. Notice these are going to go up and down. And some of you are going to probably have to have a few little helps written down. Okay, when we're finding antiderivatives, this is what we're doing, is antis, you're going to go up instead of down. So you know you're going to have to do this. Okay, now how can I go from here to here? Does this one give me this one? No. So check your answer. Oh, it does too. If I take the derivative of this, this goes, I have 1/5 here. You're pulling my chain. Okay, now let's do some that probably are a little more difficult. Oh, let's not do that. Let's do another one, like this same variety. F at x, or f prime at x, equals x to the nth. What's this turn into? This will kind of be a theorem. Divided by n plus 1. Okay, plus a constant. Plus c. Okay? Yes?
Can you do that proof that we need to know for our test one more time?
I won't do that today. Unless you want to stay after class for a few minutes, we'll do it then. Okay? Now, how about this one? F prime at x equals 1 over x. Or x to the minus 1.
It's 1.
Yeah, there.
It's x to the 0.
Okay, now somebody said ln of x. Now let's use this property up here. And this thing does come along with the thing that x is not equal to or minus 1. But now if I would try this thing, what would happen? I'm using this. I take x and I'd have to raise it to the
Minus 0.
to the 0 and I divide by 0. And I can't divide by 0. Okay? Okay? And so that's why that doesn't work. And here is a wonderful gift we have at this point. And that is, this is equal to, f at x is equal to, as someone said, ln of x. And we should do absolute value plus 6. Okay? Another one. F prime at x equals the cosine, yeah, I want that, cosine of x. Okay, that's going to be in terms of sine x plus a constant, right? Okay, let's try another one. F prime of x equals cosine of 4x.
Sine of 4x.
Times 4. Or plus 4.
Now, what do I do with it?
Times 4.
Times 4 is wrong. Okay, it's undoing your operation. Otherwise, we were multiplying by it. Now we're doing the division by it. Are you with me?
Yeah.
Okay. Now, this is the antiderivative. Let's try it out. So we have 1/4 out here, and the derivative of this here is cosine 4x, and here times 4, and now this one cancels with this, and there we are.
Really?
Okay? Now, watch this. We're going to change notation now. And we have done some summation notation. We have done some delta x notation. And we're going to tie this into this kind of notation in a few days. Okay? This is integral, indefinite integral notation. And we could do like this, x squared plus e to the x, and then we put a dx here like this. Now all this stuff is going to have a lot of meaning in a few days. This sign is going to move into this, and this is going to move into this. And you notice this is kind of the differential notation we were using a while the other day, getting the dx over there. And it will all be kind of nice stuff. And at this point, we're just getting some of the mechanics. So when we get there, this stuff is going to be pretty easy, I think. Okay? So now, I would like to, this operates just like finding the antiderivative of this. And the antiderivative, now notice here, I could have written it this way. The integral of a sum is a sum of the integrals, like this. See? And we've done that with limits, we've done that with derivatives. So, we could write it this way if we wanted to, but we could just pick it up here. And the antiderivative of this is?
X cubed minus 3.
And this one is going to be? Okay, see how that goes? Okay? What is this here? Okay, now you've got to hang with me until Monday, maybe Tuesday at the latest. And we're going to do some things we call Riemann Sums. And we'll use our TI-84 calculators and a few other things to move from this kind of notation, summation notation, to the integral notation. And we'll see how this all gets tied together. Okay? And it turns into, the antis will help us find areas and volumes and a whole pack of things. And also, I think Thursday, for a little while at the beginning of the period, I might go over a couple of conversion things. Yes?
Could you do a problem from 4.7 for the assignment? In the 50s?
You want to see a couple of those now? Okay, just a second. I will do one more to show you this. I never thought I was going to go this far today, this fast. But it worked. Okay, dx. James. Oh, let's make this a little more difficult. Put 3 here.
Oh man.
No, don't.
Too much.
You guys are good. Okay, here we go.
Too much.
This is a 2. That's a 3.
Is it?
Okay, so this is going to be,
X to the 4th over 4.
James.
okay, now. Yes. Okay. Okay.
Yeah.
Okay. Now, Chanel, which question did you have?
Like, can you do 50?
Listen carefully. Here's a little clue for one problem you're going to do, and it's problem 52. I think that's one. 52. The substitution is y equals ln of x. Okay. Which one did you have, Chanel?
50.
50. Okay. Which grows faster? And did you do it this way? Ln of x all over ln of x squared.
I didn't really get what it was. Yeah.
Okay. And now, and as x approaches infinity, who has a clue to get started? We have a cancellation right off the top.
Cancel the ln.
Yeah, but see, there are two of them here.
Yeah.
So I'm just gonna write it
Break
like
them
this.
up.
See, like this,
Yeah.
okay?
Cancel. How?
We're allowed to
So that's
cancel this
it?
time?
Pardon?
You can actually cancel, you're not gonna yell at us?
Well, it's the same number.
Okay.
No, no, you.
Okay, so can you finish
So
that?
the power is with the top.
Listen to this guy. Trevor, you said, now cancel the X's. No, we can't cancel the X's. Okay.
So does the power lie with the top one?
Pardon?
Does the power lie with the top with x
Hey,
squared?
just a second. I need concentration. I didn't follow it. Yes?
Does the power lie with x squared then? What do you do? Because ln of x, if you let it
I didn't follow it yet.
drop.
I'm sorry.
X squared has
Which
the
of the
power.
squared? So
Yeah.
X squared has the power in this problem, right?
I think so.
So it grows faster.
Well, we don't know yet. We've got some work to do.
Okay.
Okay.
Now,
Is this infinity over infinity? You have to check it because oops, and that's what I have to do to you. If that isn't the case, we can't go on. And it's infinity over infinity.
yeah.
Okay, so the first thing I'm gonna do now is take the limit as x approaches of the derivative, which is 2x over
1 over x.
1 over x. And you can simplify that.
That's the
Okay, hey guys, I forgot to do this. Will you go with me and we can get this done before the end of the class period? Page 289. 289. The pitfalls of L'Hopital.
Oh dear. Oh dear.
Page 289. Okay? Notice right off he says we are not doing the quotient rule when we're doing this. We're taking the derivative of the top and the derivative of the bottom. Don't get those two ideas confused. Okay? And that's what he's saying in the first line. And if you're normal, you like to get them confused. All of a sudden you see a quotient and say you have to use a quotient rule. We're not doing that in L'Hopital. Okay? The next one. It says be sure that the given limit involves the indeterminate 0 over 0, infinity over infinity. Every step. If you have to use it 2 or 3 times, make certain it's in that form. Okay? The next one at the top of the page. When using L'Hopital repeatedly, that's kind of what I just said. And the last one. I told you about that one in the problem where you can get into an unending cycle. And it just gets you either nowhere fast or it just gets you going the wrong direction. Okay? So those are the limits. Okay.
Donkey class.
Chapter 2.